Good day, and welcome to today's webinar on embedded at-scale JTAG-based debug of x86 servers. My name is Larry Osborne, and I'm the product manager for Asset Intertek's ScanWorks Embedded Diagnostics, or SED portfolio. Asset is the leading provider of the ScanWorks platform and hardware validation and test, and the SourcePoint platform for software debug and trace. And SED that you'll hear about today is our embedded JTAG firmware solution. Before we get started, I'd like to go over a few housekeeping items with you so you know how to participate in today's event. First and foremost, today's webinar should run approximately 40 to 45 minutes. During that time, you'll have the opportunity to submit text questions to today's presenter by typing questions into the question pane of the control panel. You may send your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. You will also have the ability to participate in polling questions, so be prepared to participate. On that note, please be sure to download a copy of today's presentation, which can be found as a handout in the control panel of your screen. Now, without further ado, we'll turn the time over to our presenter, Alan Squigna. Alan leads Asset's business development initiatives for JTAG, inclusive of debug, test, and hardware validation technologies. A prolific technical blogger and author of the Middleboard Chronicles. In his spare time, Alan also dabbles in x86 and ARM architectures and UEFI and Windows and Linux kernel hacking. Over to you, Alan.
Hey, thank you, Larry. I appreciate it. Good day, all. Let's move ahead into the agenda slide here. I'm going to do a deep dive today into the whys and wherefores of at-scale debug, JTAG-based at-scale debug, a little bit of the history, about how it came about, and then the underlying architecture in terms of the BMC hardware, firmware, software requirements needed to support this sort of remote JTAG-based debug. Then we'll dive into the use cases. We've got there are actually many use cases associated with this technology, but we'll look at a few of them: the crash dump application, hardware platform validation, for example, on PCI Express ports, UPI, and so on. And then some monitoring and telemetry applications, that are unique in the aspect of they operate on a running or an operational system. And then we have a treat today in terms of having a demo of Asset's implementation of embedded JTAG-based debug or at-scale debug, known as ScanWorks Embedded Diagnostics, or SED. And we'll actually be connected to a live Intel server and running some of the Intel CScripts, and then some on-target diagnostics using the SED framework. And then we'll wrap up and hand back over to Larry for some questions. So in terms of background, just a kind of quick refresher on JTAG. It's, as you probably know, over a 30-year-old mature technology. It's been around for a while, and the foundation of which is in the bottom of the diagram here, which shows the JTAG finite state machine over on the left-hand side. Really just a collection of data registers, instruction registers, and there are around the perimeter of the device behind each pin. There are boundary scan cells, and really only a handful or two of gates associated with each, and the collection of which acts as a serial shift register around the perimeter of the device, and also parallel shifting between the outside world, the external pins of the device, and the internal system logic of the chip. And JTAG, of course, is ubiquitous. There are billions of devices, all of which have JTAG embedded in them, and that's happened over the 30-year period as these sort of 4 application areas, test, debug, validation, programming, have evolved new applications and new technologies built around the base standard, right, to perform some extremely useful functions. All right, having said that about JTAG, how did at scale, JTAG-based debug, come around? There have been some OEMs that have been using this technology for the better part of a decade, but the technology and kind of the deployment of the technology, really gained steam back in 2017. So as part of the Open Compute Project, or OCP, Microsoft Azure made a contribution of their Project Olympus server design, right? The intent of which to support the hyperscale initiatives, of course, right? And to a great extent commoditize and open source, right, server hardware. And part of that design, right, the schematic support, and part of that design had a hardware connectivity between the some of the general purpose I/O of the service processors on those boards, the BMCs, and the CPU debug port, the CPU scan chain. So that happened back in 2017, and now this connectivity, it is optional, but it has essentially become, that connectivity has essentially become a de facto standard on all of the OCP server platforms. The BMCs themselves, you can see in the diagram, over on the right-hand side, it's an older BMC from ASPEED, the AST 2400, for example, right? Some of the commercial BMCs, you have to bit twiddle. You'll run in software mode, and you've got to bit twiddle the JTAG port, the debug port of CPU, right, to perform the debug functions. And some others, the ASPEED again being an example, they have a hardware-based JTAG masters. There's RTL, within the ASPEED BMCs that will drive the JTAG interface at a much higher rate. If you're bit twiddling, you're going to get a sustained T clock of between 1 and 2 megahertz. And but if you've got that hardware driver inside the silicon, you can get to 12 megahertz, 16 megahertz, 32 megahertz. Really, as far as you can go, really only limited by the signal integrity of the hardware design associated with the JTAG interface on your board. So once that hardware requirement, that hardware prerequisite is eliminated, it's a fairly simple matter then of throwing in some firmware into the BMC, basically a JTAG driver, and then the run control firmware, right, that initiates the debug functions, and you're good to go. And this technology is sometimes called embedded XDP. You see you're going through the XDP interface, extended debug port on Intel designs, or embedded ITP, in-target probe, some various synonyms there. Closer look at the architectural block diagram. Up at the top right, you see the typical topology BMC or any sort of service processor, ASPEED, Pilot, Nuvoton, any off the shelf, really, typically an SoC, for example, that's got an ARM CPU, maybe an FPGA fabric inside, like the Microsemi or Microchip Smart Fusion 2 can act as your service processor, and it's got the green line is shows the connection to the CPU scan chain, and those run control feature firmware that I was talking about is the thing that initiates the debug functions, which really manifests themselves in terms of being able to read and write all architecturally visible registers, memory, and I/O. Optionally as well, you can connect the BMC through its Ethernet connection to a remote host and run some host applications, for example, the Intel CScripts down right in a Python environment, running on an external PC. And that, of course, gives you access to a superset of a library of customer scripts, right, that perform a lot of useful functions. And we'll see those in operation during the demonstration. All right, just going up to 20,000 feet for a second, I'm going to highlight the debug access mechanisms, right? When you want to do JTAG-based debug on a server, right? The typical configuration, that we're all very used to is, on the left-hand side, you have some sort of a JTAG-based debugger, a hardware-assisted debugger like the asset SourcePoint product, and it's running the CScripts connected, the Intel CScripts connected over USB or Ethernet to a hardware probe, which has a commercial CPU and an FPGA, right, for performance reasons, right, which in turn is connected over a, give or take, 12-inch ribbon cable to the JTAG or XDP interface on the server. As you move into the embedded realm and put the run control and JTAG firmware in the BMC acts as a run control host, and we eliminate the need for the hardware probe. And so that gives you some benefits of scalability. Now you can still run the CScripts, but you've cut out the requirement for that hardware probe, which is of tremendous benefit because we all know, right? Sometimes there are physical access constraints. If you're walking up to a server in a rack, you may not have physical access to the XDP interface down on that server target. So you could run maybe one at a time, perhaps, or a couple at a time, right? CScripts on some servers simultaneously. In the perfect world, or combining the best of those two previous worlds, you've got what you really want to be able to do, though, right, is take some of the functionality that's running on that PC in the Python environment, the CScripts environment, and port it and have it run autonomously down on the BMC. And so you get a tremendous amount of benefits by using that approach. And as it turns out, because you don't have to do, you're not backhauling over USB or Ethernet to the remote host and running Windows and interpreted Python and so on and so forth, right? The final configuration is faster than even what you can get with a dedicated hardware probe. And now you've got target-based debug agents, and so you can deploy those on an infinite number of systems simultaneously. It's truly at scale, unlike really the first two topologies above, and also more secure. There's you're eliminating the need for the remote host. You're cutting out the Ethernet connections, so those potential attack surfaces are mitigated in this approach. All right, I'm going to pause and take a breath, and actually, maybe Larry, is it good time for a polling question?
Yes, it is, Alan. Thank you. And our first polling question is: are you currently using JTAG for any benchtop-based debug? Please select the appropriate response and click Submit. It looks like about 2/3 of you have responded. We'll give those of you who have not yet responded, go ahead and submit your responses now, and we'll close the poll in a minute. We are now closing the poll and share the results with you. So 63% of you are currently using JTAG for benchtop-based debug. Back to you, Alan.
All right, thank you, Larry. All right, that's interesting. So just almost 2/3 are using JTAG. So yeah, those of you will get, I think, understand clearly some of the benefits of moving away from a benchtop JTAG-based debug paradigm over to an embedded paradigm. Yeah, so looking at that host target topology at a lower level of detail, what we typically have here is on the left-hand side, the Windows PC, the host, what we call the host, is running the Intel CScripts, for example, right, and the associated Python command line interface. That runs through some middleware that Intel provides called OpenIPC, which in turn connects to a probe plugin. And OpenIPC, so with the associated probe plugin, allows that left-hand side to connect to an arbitrary probe, right? And we'll put that word in quotes, because that arbitrary probe could be, for example, you're running Intel CScripts with a hardware probe, the Intel Blue Pod, or the Asset Arium ECM XDP3E hardware pod. And in this topology, the SED topology, the pod, quote unquote, is actually a socket server, which in turn connects to the SED API, the library itself. So the socket server is just taking commands from the host and funneling them down to the invoking the API and executing the embedded ITP run control library, which in turn issues the needed JTAG scans and sideband signaling needed by the Intel hardware to perform run control. So this is the remote Intel CScripts approach. If you can actually cut that cord, as I showed in the previous diagram, and eliminate the remote host requirement and run what are called OTDs, or on-target diagnostics, you can take some of that functionality, for example, the Python-based CScripts, and port them over to C or C++, and run them, compile them, and then run them natively down on the BMC. And that, of course, is only possible if you've got access to the API, right? In our case, the ScanWorks Embedded Diagnostics, or SED API, and this has the benefits of speed and scalability and security that I mentioned on the prior slide. As a matter of fact, right? The BMC is now running autonomously, without the having a backhaul to any sort of a remote workstation. So in the asset case, the SED API library is a fully documented, fully supported API that people code to, and if you're writing an on-target diagnostic or OTD, you do invoke the API, of course. There's about 80 API in our library, and all fully documented. The image at the left, at the top there, is really just an excerpt out of the table of contents associated with our API. There's anywhere from low-level functions like the scan DR, scan IR, scanning the data register and scanning instruction registers, or higher level functions such as setting the active CPU core thread, setting breakpoints, machine check breakpoints, SMM entry breakpoints, and so on. All of the things that you're familiar with from a run control perspective are provided by the SED API. And the document itself, the reference manual for the SED API, is available under NDA, and there's tons of source code and program examples therein. To see the sort of the public version of this information, you could go onto our website and go onto our blog section there, and there's 4 articles there, parts 1 through 4 of coding to the SED API. All right, let's see. Let's go into now some of the use cases right before the demo, right? Because we're going to show crash dump, and this is a really interesting and powerful use case, for embedded JTAG, because of the fact that these are the kind of bugs when a system crashes or wedges or hangs. These are the most difficult, intermittent, random, really hard to triage kind of events. And of course, when the platform is locked up, the operating system, right, and platform firmware, not available to run any of a plethora of diagnostics that you might have available. So you really want, for the best kind of crash dump debugging, right, you really want an out-of-band forensics retrieval methodology, and those two really are PECI and JTAG as part of the table. And JTAG, of course, is the better than PECI, certainly the fastest. It's supports a much richer set of functionality than anything else. And the BMC is just the natural candidate for any sort of a autonomous crash dump, autonomous data retrieval. And I'm going to take another breath, Larry, I think, and hand over to you for another point.
Okay, Alan, thank you. So our next question is, have you ever run Intel crash dumps? Please respond and submit your responses, and we'll close the poll in just a few minutes. I see that about 40% of you have not yet responded. Go ahead and submit your responses now, and we'll close the poll. We are closing the poll now, and I'll share the results. So it looks like 70% of you have yet to run Intel crash dumps. Back to you, Alan.
Okay, that's a higher percentage than I would have thought, but okay, interesting. But the concept is there, right? In any event, this is a very popular C script and actually a fairly popular PECI-based approach to in terms of getting crash dump information, and and the OEMs use it all the time, especially during early silicon early platform bring up when platforms tend to be servers tend to be a little bit unstable. Right, and it's useful, of course, throughout the life cycle of the product. Second use case is platform validation, and an example of this is PCI Express, stress testing, where you exercise, the link training and status state machine, the LTSSM. There are C scripts for that, and what you want to do ideally, Intel has written a bunch of features to. As you'll see, I'm going to run this thing interactively, as you'll see shortly. And what you're trying to do is to detect design marginalities, design defects, right? Either in the board design itself, or some of the firmware within the PCIe upstream and downstream components, and identify, especially when you change HBAs, right? New components, new steppings, new firmware come into the picture, right? You're trying to avoid that surprise link down nastiness. And then finally, monitoring your telemetry. JTAG is ideal for this because it's at the hardware level, and with some of the newer functionality within the Intel platform, the Intel CPUs, such as the OBMSM, the Out-of-Band Management Service Module, you can use JTAG and not actually have to halt the target. Right, the platform can continue to run. And you can extract machine check, CPU, and downstream PCI configuration space, via MMIO, or reading those registers just in the background as part of telemetry services, right? So, and then, you've got examples of where you do that in the background initially, right? There's an event, and then you halt the platform, using full run control to get all the rest of the data that you'd like to get out. All right, so the demo. So we're going to jump into the demo now, and really the essence of this demo is, for the 3 use cases that I talked about, right? I've got a total of 5 Intel C scripts to run. All right, PCI topology, check members, the LT loop, as well as PCI devices, and a JTAG-based autonomous crash dump. So in the demo, we're going to run the C scripts initially via SED. So there's no hardware probe in the picture. It's just a direct Ethernet connection from the remote host into the BMC, right? And then the real treat is I'm going to do the same thing again, but this time, right? We're going to run on-target diagnostic versions of these C scripts. Right, so all of these Python based C scripts, and there are hundreds, thousands of lines of codes, probably total. We've ported from Python to C, and we're going to run them directly down on the target, and you're going to see how much faster they run, and just get a feel for how powerful the on-target diagnostic model is. So. In the demo itself, I've actually recorded a video of the demo, right? Because some of these C scripts take a long time to run. So in the interest of not watching the grass grow green for a while, right? I've accelerated, right, the demo, and I'm just going to switch over to the video and just play it and talk over it and tell you what you're going to be seeing. So here we go. Let me make that a little bit larger for everybody. There we are. All right, so what you're seeing here is the serial console into an Intel server that we have running in the background, and we're just sitting in the UEFI shell, and we've got access to the BMC as well. I've got a serial console PuTTY connection, or the window you see right now, into the BMC. This is an A-speed A-speed BMC, and I'm running that socket server application, as you can see in the background. And the socket server is just sitting there quietly, waiting for instructions to come down from that remote host, running the Python CLI and the Intel CScripts environment, and then it'll take that information, blast it down to the SDAPI library, right? Invoke the run control functions, and then funnel the information that it retrieves back and forth, right, to the remote hosts as well. All right, so right now it's sitting and it's processing data in the background, and we also have the Intel CScripts environment live and up and running in a Windows command window here. And you can see we're just sitting there, and this is the standard preamble that you see when you run the CScripts. Within the CScripts environment, you can run, for example, the itp.device list. This is a little application that just, a little script that just runs, scans the JTAG chain, the CPU, and shows you all the devices that happen to be there. There are higher level functions, of course. Intel has done a good job. They've got a lot of built-in help into the CScripts environment. So that funcs command or functions command shows you, there are a bunch of different modules here, such as Clacson and memory controller and Uni, short for Unify, and PCI Express and PCI, and so on and so forth, that have a bunch of functions therein. So there's literally hundreds of things that you can really do. And with the built-in help, you can do a uni dot with tab completion, to show an abbreviated version of the number of functions in that module that are available to you. And you can type in a help command at any time, uni dot, and then call out the specific function you're looking at, and it'll give you some short and simple help associated with that. So get bitrate, obviously, you just specify the socket number, you specify whether you're talking UPI or PCIe, and that'll dump out the bitrate of the link, right, in gigabit per second. All right, so that's the backgrounder. Let's look at the PCIe module, because that's got a lot of useful functions inside of it. And the one that we're going to start with here in terms of running a CScript on is the PCIe.topology. That's a fairly simple CScript that simply just goes out there, right, scans the platform and displays a table, right, with the PCI ports, listed. And the way this CScript works, it doesn't have to do this, but the way the CScript works is it actually, hauls the first thing it does is hauls the platform, and it wants to set itself up, right, to use run control. You could conceivably do some of this stuff or all of this stuff with OBMSM, but this is just how this CScript works itself. So it goes in and it's going to halt all cores, all threads, here on the platform. Now it's going to take a couple of minutes, so I'm going to accelerate it a little bit and just jump to the results, because and I'm going to kind of do that consistently throughout the CScripts portion of this demo, just in the interest of time. So bang, that did it. We got to the end, and that ended up taking 2 minutes and 42 seconds to run using the SDAPI scripts. I'm going to make the window bigger here so we can see exactly what's happening. And there's that table, right, of the PCI Express port mappings. So we see the information associated with width and speed and vendor ID and all that fun stuff. We've got a couple of PCIe cards in here at port 1A and 2A, an AMD card, graphics card, and a PCIe card from AS Media over in 2A. So that's the PCIe.topology CScript. Nothing fancy, nothing you couldn't do yourself at home, right? But it's just nice. It's just one of the hundreds of different things, right? I mean, Intel, of course, uses the CScripts for silicon validation. Let's look at PCI with tab completion. So there's a ton of functions under PCI, and we're going to want to do a PCI.devices is what we want to do. What we would like to do in this example is just print out all of the PCI devices that are on this particular platform. So with the help, you see, what it does, right? It's pretty simple, right? It's just going to print a table of the scan PCI devices, and because these things tend to run a little bit slowly, Intel has broken them up into two parts. Really, a PCI.scan that you've got to do first, that goes out and scans the whole platform, right? And then you do the PCI devices. So I'm running the scan now. And if you look down at the bottom, you can see it's walking through segment 0, of course, right? Bus 0, all the buses, devices, functions, one by one, right? And collecting the information and quietly storing it away so it can be used by the other PCI sub-functions there. So again, I'm going to speed it up because once the scan is complete, things get interesting, and then we can actually print something out. So there, it went through all 255 buses, 88 devices, 248 functions that are on this platform. So there you see the output results. Now I can run the PCI.devices, and same thing. It's going to run and collect all that data and print it out to the screen. Now it took about 8.5 minutes. I accelerated, of course, and I'm accelerating the PCI devices too, right? It took about 8.5 minutes to run the scan, and it took about 8.5 minutes actually, as you'll see when we complete the PCI.devices. And it dumps out, 2 tables. Really is how this one works. And one is, of course, just listing the BDFs, and then the second table is the endpoint information. All right, so that is PCI. Again, nothing fancy, but when you're doing silicon validation, right, and when you're at a hardware level and you need to see what's going on, this is pretty useful. Clacson is the next section. Clacson is it's a module that has a bunch of functions that dump errors, check and dump errors, machine check errors, PCI Express errors, UPI, and so on. And I'm going to run the Clacson.check mem errors here, right? And that's going to go out, and it's going to look at the platform, and it's going to go across those 4 memory controllers, right, as listed there. And it's going to look for any sort of memory errors. And this platform has got, it's a good size. It's got 144 gig of RAM, right? So of memory. So it actually takes several minutes in real time. That I've actually going to accelerate myself, because I happen to know that I've run this program many times, and it runs a little over 8 minutes. 8 minutes, 1 second, couple of seconds is typical. And as you would expect, there's no errors found. This platform is good to go. We haven't injected any errors or anything like that. So no errors found, and pretty much that empty file is putting into the CScript puts it onto my documents folder. All right, so those are kind of workman's sort of CScripts. Let's look at something more interesting. That being the PCIe.lt loop, the link training loop, right? The link training stress machine that I talked about earlier, right? And there's a lot of good help, obviously, on this thing, right? I'm going to run that LT loop PCI Express stress test on socket 0, port 5. That's the one we had the graphics card in, right? And it's test type 1, which is a basic link retrain. And we're just going to run one loop in this example, right? Because this does take a fair amount of time, and I'll have to accelerate it as well, right? And once it finishes its initialization, just simply because when you're running through SED and you've got that Ethernet backhaul, right? You've got the scalability, but it's a little slower than if you had a dedicated hardware probe, sort of admittedly. Right, but you've got more scalability because you can actually run this test, without the requirement for the hardware probe, which is kind of cool. So yeah, basically we're knocking down that link, port 5. We're knocking it down. And then we're letting the system retrain it, and out comes the output. And as expected, no errors. in upstream or downstream components, and it took a total of 63.5 seconds, to run that one loop. So what you probably wouldn't want to do in production too much, right? Just the amount of time involved. You really want to run hundreds, thousands, 10,000 loops to really stress the link and look for those intermittent bit errors. And we'll see the solution to that now as after we do the crash dump C script and turn our attention to the on-target diagnostics. All right. So crash dump, last but not least, really popular C script. We need to first do an error injection on the platform and lock it up or induce any sort of error, right, for crash dump to provide some useful information. So in this instance, I'm going to inject a machine check error, an MC error on the platform. This is the C script itself, right, that's doing this. And the way that this works is it wants to halt the platform, and then it's going to access an invalid memory range, right, and therefore cause a machine check exception. And there it goes, it's done. All right, so we injected the error, and now we can use the Intel crash dump C script to pull out all of the information, all of the breadcrumbs out of the platform that we can, and learn what was going on, right? And you can look at all of this data, and if you're really good at x86 architecture, you'll figure it out yourself, or you'll send the data to Intel and they'll help you figure out what's going on. So I use a little trick here just to time it, because I do happen to know that crash dump takes a very long time, can take a couple of hours really with a bench prop probe, and I happen to know it's going to take close to 10 hours to run over the SCD interface, and a whole lot faster than that when we actually embed it as an on-target diagnostic that I'll show near the end. So crash dump, the first thing it does is it puts the platform back into a running state, and then you can see down at the bottom, I'm going to speed this up as well because we're not going to sit on this webinar all day. It goes out and collects the register information, right, on the bits of IP within the Intel CPU that it's interested in. So the first thing that it does is it goes out to each and every core, right, and extracts a bunch of register information out of there, right, for all the associated sockets, cores, and threads. Then it's going to go out and pull out the machine check architecture information. Then it's going to go out and get the table of requests, right, or TOR dump data associated with the caching home agents. And then when it's finished that, it's going to go out and get a bunch of the other things, power management information, a big core. And then ultimately at the end, it's going to dump out all of the uncore information as well. And that takes a large amount of time, right? And so you can use the C script, right, in this instance, when you're not in a hurry to get the platform up and running. But if you want to suck out all the data as fast as you can, right, and then return the platform to service, so it can do some more useful work, right, you want to use the on-target diagnostics approach that you'll see in a bit. So I'm going to super fast go through this thing and complete it. And there you see 35,263 seconds, so a whole lot of time. And it puts the output of the data into a JSON file format in my documents folder here, and we can just take a little look at it, right? This is sort of a standardized format from Intel that has some preamble information, right, at the top, but it puts all of the crash dump data, and there's a ton of it, right, into this JSON file. And you can then do a summarizer afterwards, right, and translate this out into something human readable. All right, I'm going to take another pause here and take a drink of water. And before we jump into the on-target diagnostics, so that was the C scripts. Now we're going to jump into the on-target diagnostics portion. So I'm going to hand over to Larry in the meantime and for a poll question.
Okay, thanks, Alan. So our third polling question is, do you use LT Loop CScripts to do PCI Express stress testing? Please select the appropriate response and click Submit. It looks like about 30% of you have responded. Those of you who have yet to respond, go ahead and submit your responses now, and we'll close the poll in a few moments. We're now closing the poll. And the results of the poll is 89% of you have not used the LT Loop CScripts to do PCI Express stress testing. Alrighty, Alan, back to you.
All right, good, Larry. No, that's interesting too. Yeah. I mean, typically, PCI Express hardware validation is often a different group within the company, right? All of these ODMs have hardware validation teams, right? To stress test and look for performance and conformance of the platforms, especially when it comes to some of the high-speed buses and memory. All right, I shall fire it back up and continue. And so now we're going to look at the OTD. So I controlled seed out of the socket server. So I'm now just sitting in Linux, right? There's no longer any communication between the BMC and the remote host. We're just raw native down on the BMC itself. And I have this PCIe topology application, right? That just ran like pretty quick, as you can see, 0.949 seconds. So that PCIe topology did the same thing as the PCIe.Topology C script that took, what was it, 2 minutes, 42 seconds, right? And we do it in less than a minute, less than a second. Same thing with PCI devices, right? This is now running in C as opposed to Python, no remote host involved. And remember, PCI devices, you had to do the scan first and then the PCI.devices, right? We just collapsed those two functions into one on-target diagnostic, right? Just because it's so fast, right? I mean, there's no longer any reason to split up the functionality. And in fact, now we're dumping out the table, identical in format as what you had seen with the C script itself. And in fact, this thing would be done, the application, the OTD would be done if it wasn't for the fact that we're spewing out the console and slowing ourselves down caused by the back pressure associated with the serial port. All right, if we were running this into a file, it would be a whole nother story, right? So it's going to do the same thing as before, run through the bus device function, all the PCI configuration space, and just put it all out. And it took, if you recall, about 17 minutes. I'm going to summarize this at the end, right, on a graph, right, in terms of performance of the different approaches, but it took about 17 minutes to run it via CScripts. And here it took 74 seconds. So a whole lot faster, as a matter of fact. All right, so just walking through each of those CScripts one by one. We're going to apply the time as well to these, and that Clacson dot check mem errors, same thing. And in there, instead of taking minutes, 8 minutes, 1 second, we got it done in 1.249 seconds, right? So the performance of the on-target diagnostics is orders of magnitude better than what you would see, right? When you've got all of that extra overhead. LT loop, we're going to do the same port, same PCI Express card on first socket, port 5, test type 1. But instead of running one loop, you see the final parameter, we're running 1,000 loops. And we ran those 1,000 loops in 3.609 seconds compared to the 63.5 seconds that were associated with the one loop using the C script, right? So that's of course a huge difference. Now the crash dump, again, a two-step process. We have to do an error injection, and we're going to inject. We wrote our own application invoking the SDAPI library that does that same thing, an error injection, machine check error, and that's done. So now we can run the JTAG-based ACD, JTAG-based autonomous crash dump. Not PECI. This is running right down on the BMC, no remote host connection back. And remember, it took close to 10 hours to run on the CScript. And here I'm going to redirect the output into the crashlog crashlog.txt file so we can look at it in a moment. And it's going into the big core, the machine check architecture, uncore, table of requests, power management info, address map associated with the two sockets. And then just using the Linux more command, you can see same data, right, in the standardized Intel JSON format associated with the crash dump. So super fast, right? Yeah, so you could, I mean, hypothetically collect a ton more data if you wanted to, right, by having this embedded down on the BMC, as opposed to trying to do this remotely, right, with the overhead of a hardware probe and the umbilical cord and so on and so forth, right, between the host and the target. All of that is eliminated by going with the OTD approach. All right, I'm gonna now, so that's the end of the demonstration. I'm gonna jump back into the PowerPoint slides just for the wrap up. This slide summarizes the benchmark results of the CScripts versus the on-target diagnostics, right, in terms of time. So what we have on the left-hand side is, so we can see everything somewhat to scale and fit everything on one page, a logarithmic scale, a power of 10 scale in terms of the number of time, the amount of time that it took to run the CScript in blue, right, or the on-target equivalent on-target diagnostic in green. So as you can see, for the PCIe topology, the CScript took 167 seconds to dump the whole thing, about 1 second actually for the on-target diagnostic. So a little bit of a a little over 2 orders of magnitude difference between the two. In other words, the OTD is 100 times faster than the CScript in this example. PCI devices, 1,024 seconds versus 74 seconds, so a little over 1 order of magnitude. Check mem errors, 481 seconds versus 1.25, so 2.5 orders of magnitude, or almost 500 times faster, right? I mean, the smaller the candle, the better, because it's a shorter period of time. The LT loop is a really interesting one, because 36.1 for 10,000 loops, right? It would take the on-target diagnostic 36.1 seconds, right? Whereas a huge amount of time, of course, with the SED-based CScript, right? And so that would be pretty painful. If you wanted to run 100,000 loops, hypothetically, you really want to stress your platform, improve quality, reliability, avoid the surprise link down stuff associated with CPU component or design marginalities. You could run 100,000 loops in 360 seconds or 6 minutes with this methodology, right? Which is amazing, at the risk of sounding a little immodest on our behalf. And then the crash dump, hours and hours, right? Not really practical, of course, and 7.1 seconds there. So that's 1, 2, 3, almost 4 orders of magnitude difference there. 1, 2, 3, 4 orders of magnitude there. Factors of 100, anywhere from 100 times to 10,000 times faster if you go the OTD route. And the OTDs, of course, give you the scalability, right? You could have dozens, hundreds of these things running simultaneously in the background in your lab as part of your platform validation or test or debug methodologies. And you don't have the Ethernet stuff. So and you don't have that remote host. So you're reducing the overall attack surface of the technology. So speed, scalability, security. For more information, I mean, you can of course pull the handouts down from your control panel, but we've done a couple other webinars with the UEFI forum on some of this technology, right? On the AMD side, on Intel side, Intel architectural event trace capability. And if you really want to know more about what you've seen today, best route is to go to the to our blog section of our website, and it's broken out in categories. So click on the embedded diagnostics category, and you get a lot of really hopefully interesting articles that deals with the informative articles that deal with the technology. All right, and last slide. That's the there's my contact information. Do feel if you have any questions above and beyond what we cover here today, feel free to email me, and I'm on LinkedIn and Twitter. Drop me a note there as well, and I'll respond quickly. And that's it for the demonstration and presentation. I'm going to hand back over to you, Larry.
Thank you, Alan. Now we're going to begin answering some of the questions submitted during today's presentation. As a reminder, you can still submit questions through the question pane in your attendee control panel. Alan, our first question is, are Intel trace features supported by SED?
That's a really good question. Yeah, so the answer is a qualified yes. As a background, I mean, Intel trace features are things like LBR, last branch record, and Intel processor trace, and architectural event trace, right, and a few others, right, and all of those trace capabilities are accessible via JTAG. So that's really the good news, right? I mean, and in fact, yes, some of the trace capabilities on the Intel silicon in particular, such as AET, require JTAG. Right, will only work with JTAG because there's some pro mode MSRs, right, that need to be extracted or written to. So yes, the short answer is yes, right. I mean, we may not have implemented technology support for all of them, but the short answer is yes. Any feature accessible via JTAG, which is all of them, can be supported on a BMC equipped with SED.
Alrighty, our next question is remote source level debug supported?
No. So the answer to that question is no, right? The applications that you've seen today is running the Intel CScripts and the On-Target Diagnostics, right? You cannot really connect to the BMC target with our, we have a source level debugger called SourcePoint. Right, and SourcePoint you can't connect to the BMC target, via our SourcePoint source level debugger. The intent of SED is really for like at scale, remote, forensics testing, right, and autonomous debug via the OTDs.
Alrighty, one final question. It's a very interesting one. Isn't embedded JTAG inside of BMC considered a security risk?
Oh, that's a good question. Yeah. How long do we have, Larry?
Just a few seconds. We're running out of time.
I'm running out of time. Yeah, so I'll be brief, right? I mean, yes, that's a really good question. It's something we're asked about all the time, right? There is no question or no doubt that JTAG is a very powerful technology, and if you equip, right, a BMC with JTAG and with run control, right, you're equipping the BMC with certainly a lot of additional functionality. And there's always that trade-off between adding new functionality and security. They're really two sides of the same coin, right? Do you want to be able to test your platform, right? Or do you want it to be locked down and frozen, right? It's certainly a requirement that the BMC should be at the hardware root of trust, right? I wouldn't mess with this stuff if your BMC, was not part of the chain of trust. But ultimately, it really revolves around the use cases, right? I mean, some of our customers solely use SED in the lab environments, right? And don't make it the hardware or the firmware part of production. And really, if you use the on-target diagnostics approach, you're mitigating against attack to a great extent because the BMC is entirely autonomous. So again, if it's part of the root of trust, you're good to go. So yeah, I would kind of wrap that this up by saying, with yes, with great power comes great responsibility.
Thank you, Alan. It looks like we really are running out of time. In fact, we've gone beyond. Alan, is there anything else that you want to cover before a wrap up?
No, I don't think so, Larry. Yeah, thank you very much. And thank you, everyone. It was a pleasure being with you today.
Thank you, Alan. And thank you, everyone, for attending today's webinar, Embedded at Scale JTAG-based Debug of x86 servers. If you have any other questions, please make sure to make a note of Alan's contact information listed on the last slide of the presentation. As you exit the webinar today, we would appreciate it if you would complete a survey on the presentation and provide your feedback. We'll also receive a follow-up email within 24 to 48 hours with a link to view of today's recording. On behalf of Asset Intertech and our presenter, thank you for joining us today and have a great rest of your day.